Alrighty, so we're going to go ahead and do problem 1 here, and I wanted to start with just a video of what you're expected to, what this reaction is. And so sodium reacts very aggressively with water because if we think back to those good old electrons, sodium really wants to give up electrons, so it's a really unstable metal. So that's kind of what happens. It's a giant explosion, and so there's a few things that we learned just from that video. The first thing that we learned is that, sorry, excuse me, I already gave it away here. The first thing that we learned in that video is that sodium will, reacting with water, will create a big gas. Well, that gas is hydrogen gas. It will, obviously something has to happen to the sodium, and so we'll talk about what else is going on, and then it clearly is getting rid of energy in the form of that explosion. So if we start by writing the chemical equation, we have solid sodium plus liquid water, and that's going to react to form sodium hydroxide and hydrogen gas. So sodium hydroxide is aqueous, hydrogen is gas, and clearly there was a large amount of energy at the finale of that. So obviously that energy, that heat, that fire, that explosion that we saw was not due to us putting that there. It was instead a product of the reaction. So when a small piece of sodium metal is dropped into a beaker of water, hydrogen gas and a solution of sodium hydroxide are products. Solution becomes warm. So what you can see is that everything is pretty well represented here. We have our energy, solution becomes warm, we have sodium hydroxide. What kind of reaction is this? It would be single displacement. Alright, and so now what we have to make sure that we do is that we balance the equation. So if you go ahead and add up the atoms, you can see, because you never know, sometimes you start that way, one sodium, 2 hydrogens, three hydrogens, 1 oxygen. So the question becomes, how do we go ahead and balance this? So one thing that we know is that H2 is only in one place, and we need an even number of H2. So if we start by adding a 2 here, that gives us now 4 H's, but it now also gives us 2 sodiums and 2 oxygens. So if I go over, now I have to add a 2 there. Now I'm at 4 hydrogens, 2 oxygens. That's great. So my oxygens and my hydrogens match up. My oxygens and my hydrogens match up. Now the only thing is, do my sodiums? No, I need a second sodium. So great, balanced equation. Here we go. Drawing the energy. So if I start with 2 boxes each, because that's how we start, I'm looking at what happened in that reaction. So did I add something to the reaction in order to cause it to progress and actually have a reaction, like this sodium hydrogen carbonate or sodium bicarbonate where we were adding heat? Instead, no, you just put sodium and water into a container together and a reaction occurs. So what this means is happening is that clearly chemical energy, because of this heat as a product, chemical energy is causing that reaction to happen. And one of the things I had mentioned was that sodium is very unstable. So that unstable is connected to the amount of chemical energy. It's like, I think I made the analogy about the child going a million miles a minute and bumping into things, and that's what sodium's doing. So sodium has this built-up chemical energy within its molecules, and that chemical energy immediately gets converted to thermal energy. The reaction is instantaneous. You don't need to add anything. So I'm not going to add anything into this bar here, and instead what I'm going to do is I'm going to go back and I'm going to say, all right, so I added a bar of thermal energy and I lost a bar of chemical energy because, again, everything has to be accounted for. And then the explosion that I saw was that thermal energy leaving, because again it's going to inevitably go back to that base temperature. So my thermal is always going to start and end in the same place. My chemical is now lower, and thus the energy that left, because all 4 bars need to be accounted for, that thermal energy was released as heat. Okay, so this right here is what we consider heat of the warmth of the test tube. If I were to do a chemical energy curve, I start with higher chemical energy in my reactants than I do in my products. Like my products clearly end with lower chemical energy than they started with, ending with 1 bar, starting with 2 bars. All right, moving on. So now, again, I have a balanced equation. I know so many things. I know the reaction, I know the style. That equation gives me so much information. So now we can go to actually problem solving here and say, okay, so I have 5 grams of sodium metal. How much hydrogen gas would I be able to create? So I know what I have. So I always start with, here's what I know, and what do I always need to get it into? I need to get it into moles, because 5 grams of sodium in no way compares from a gram mass level, and so I can't answer that question. There's an error in the question. I should never ask how much. So I can solve for both, or yeah, might as well just solve for both here. Not a big deal. So I have 5 grams of sodium. Need to convert it to moles, so I'm going to put grams on the bottom. If I go to my periodic table, sodium is right over here in the first column. You see there at the bottom, 22.99, close enough. We can round to 23. 23 grams. 23 grams of sodium is 1 mole of sodium. Great. What does that give me? I, of course, didn't grab my calculator. So 5 grams divided by 23 moles is about 2.18 moles of sodium. So that's how many moles of sodium I'm using. How much hydrogen gas am I able to create? So now I have moles. So now I have 0.218 moles sodium. I'm trying to figure out hydrogen gas. Go back up to my equation, which tells me everything. So I use every 2 molecules of sodium give me 1 molecule of hydrogen gas. So I come do my mole ratio. 2.18 moles of sodium. That's 2 moles of sodium needs to be on the bottom, so my units cancel. Will give me 1 mole of H2. So again here, the reason it needs to be here is because now I can cancel out those units, and if I do 0.218 divided by 2, I now have 0.109 moles of H2 produced. If I needed to convert that to grams, I would take that 0.109, because again, this word how much, that's terrible. Do I mean moles or do I mean grams? I will much better about the question asking on that one. But anyways, you can do it both. So here I've found moles, so if that's what I'm asking for, we stop there. If I'm asking for grams, then I say this is how many moles I have, times 1 mole of H2 gas, this is a super easy one, is 2 grams of H2. And interestingly enough, I go right back and it's 0.218 grams of H2 gas produced. Okay, so that's the answer to that first question. Again, the biggest thing here is if you're given grams, the first thing you have to do is convert to moles, because that's our standard of talking. You can't talk about things in relationship to grams because they simply weigh different amounts, and so that is completely inconsequential to the number of particles interacting with one another. So if given 13 moles of sodium and unlimited water, which reactant is limiting, which is in excess? How do you know? So this is a situation where I know the amount of moles I have and I have unlimited water. So this one's easy. 13 moles sodium is my limiting agent. My excess is going to be water, because unlimited is going to automatically equal excess. So the thing that I want to do in this video, though, is show you, all right, what if I had 13 moles of sodium and 12 moles of water here? Which one is limiting? So 13 moles sodium versus 12 moles H2O. So if I come back up to my reaction, which is so important, what do I notice? I notice here that my mole ratio is 1-to-1 between sodium and water. Okay. However, there's a big thing here. You also have to keep into account the products here, right? So in this particular case, I can look at each of the ratios and determine how much sodium or how much of the products I can make. So for example, sodium, I could make, the only place sodium is in sodium hydroxide. So that's 1-to-1. So I could make 13 moles of sodium hydroxide. That's great. But let's take a look at this. I have 12 moles of H2O. But how many where do those H's go? Well, take a look there. It's a 2-to-1 ratio. So you have to keep that involved. That was one of your test questions as well. So keeping that mole ratio involved, how much could you actually make? What's the limiting factor in that situation? So in this case, for two reasons. First of all, because sodium and water are a 1-to-1 ratio. And second, because you have a 2-to-1 ratio between water and hydrogen gas. If I looked here, we already know that it's going to be water. If I look here, for every 2 moles of H2O, I get 1 mole of H2. So what does that mean? That means I can get a total of 6 moles of H2 gas. All right. Whereas the sodium, if you had looked at that, it could create 13 moles of sodium hydroxide. And then if we talk about the water, because these are a 1-to-1 ratio, like the mistake that you don't want to make is that water can make 12 moles of sodium hydroxide. Certainly it can. That's still less than the 13. So this here would be your limiting reactant in that case. So again, using your mole ratios, trying to figure out what's going to be the limiting factor in that reaction. That's a hard one in terms of limiting, and I would give you something a bit more straightforward, like on the quiz. But just know that if you ever see amount of moles and unlimited is always the excess. Okay, moving on. Say I have those 13 moles of sodium. How many moles of sodium hydroxide would I be able to produce? This is what I was just talking about up above. For every mole of sodium, I can create 1 mole of sodium hydroxide. So I'll write out the math because you should. Technically, it's 2 and 2, sorry. All right, and that gives us 13 moles of NaOH. So again, going back, where am I getting that ratio? I'm getting that ratio up here. Sodium with sodium hydroxide, a 1-to-1 ratio. And so now I can know that if I had 13 moles of sodium, theoretically with that unlimited water, I would get 13 moles of sodium hydroxide. Let's see, can I think of anything else that would be beneficial? Not really. Okay, so hopefully this was helpful, and I'll go ahead and do question 2 in a different video.